Jeroen Lamb from Imperial College of London. Jeroen, thank you very much for accepting our invitation. Your stage, please.
Okay. Well, thanks everyone for staying till the end. My computer also collaborates. Good. Yeah. So thanks very much for the invitation to come here. This is not my usual audience, but I'm very happy to switch gears and speak to different people. So the talk resonates with the meeting, and it's kind of a survey of some things that we've been doing over the last maybe decade or something like that. But I'm a bit slow producer, so a lot of things were known a long time ago, and they appear only recently. So I will talk with the take-home messages. That's what I say to my students: is make sure that they tell them in advance what's coming, and then in the end repeat, so that there's some hope that people will understand. So what do I try to get across in this talk? First of all, and this resonates, I think, with the talks we have seen. I would like to argue that systems with noise can, or maybe should, be studied from a dynamical system point of view. So many people seem to have trouble. They have something without noise, with deterministic systems, and then we put some noise, and it seems to be that we're in a different universe. Suddenly, we don't really know what to do. We just do some simulations. We look at some pictures. And the second point I'd like to make is compartment models may provide useful insights in terms of reductions of systems with noise. I think you could also do without noise. And Rico this morning already hinted at that this could be useful. So I'll try to kind of put some tools there. And third, I would like to talk about topological aspects of systems with bounded noise, and that they can be studied using actually traditional dynamical systems and bifurcation theoretical methods, which is maybe somewhat of a surprise. So that's not obvious that that's possible. Okay. And so, of course, this can be then used generally to study random systems, when, of course, also metastable states, transients, and stuff like that. So they provide insight. That doesn't provide answers to all questions. So what I mainly try to show is that actually it is possible to do mathematics at this level. Not that I answer all the questions, or that all the questions I answer are interesting. That's up to you, not up to me. Yeah, but I think you can do some things where I think maybe it's not obvious that you can do things, and I will try to link back to comments that were made during the meeting. One nice thing is being the last speaker is that I can reflect on everything that has happened before me. Okay, so I'll do my best to do that. Okay, so this slide maybe is not necessary, just as a general reason why I started doing dynamics with noise, because I got people that knocked on my door and asked me questions, and they say, I want to understand something. And then they came up with some things with noise, and I did dynamical systems, and I don't really know what to do. So I say, very good question, but I don't know what to do. So I thought, okay, it's interesting to do that. And there's a lot of topical applications, like the ones that we discuss here, that they seem to be relevant. And I think there's a certain kind of, maybe not in all communities, but some communities, I think people just don't want to see very simple models for things that look more complicated than the data. So whether or not that this is relevant or not depends. And sometimes it may be relevant, sometimes not, but at least this is some kind of idea that maybe we should do better. So my motivations for noise are fourfold maybe. So let's start with the last one. I think that sometimes when you add noise to a system, it becomes easier. For many people, they would say it becomes maybe harder, but as long as you know what you do, it could actually become easier. It could actually effectively account for modeling uncertainty, like the errors in the equations maybe, rather than say that it's some external thing that goes on. So I think if you have a modeling uncertainty, why not actually take a model with noise, which maybe hopefully in some sense gives a better thing than just an arbitrary model which is just banged to death about certain details. And of course, the usual things that you maybe ignore some degrees of freedom, and that's why high-dimensional systems could be reduced to low-dimensional systems, or maybe there's real noise of some kind in the system that drives your system. Yeah? So there's all kind of these things. So what kind of things am I thinking of? Well, for instance, stochastic differential equation of some type. It's not my favorite type of model, but you can look at that. There's some issues with that, but this is of course the kind of model many people here come up with. They have some deterministic system, they say with noise, and they just add plus sigma dw, and then they try to make some sense of it. But I think you can also do other differential equations where you just drive it, you make it non-autonomous, and you just drive it with some signal which maybe is the output of another stochastic differential equation or something like that, or whatever. And you can just try to understand these things. Or a very simple model of the last type in discrete time, you can iterate a function and just add a random variable, say for instance in a ball, with support in a ball. So you just iterate, and every iteration you make an error. Okay, so I think it's nice if you do things with noise, you look at nice noise, not that, because in some sense if you add noise, of course it could be, everything becomes harder, potentially, but if nice noise helps us. So I would say, before we start to complicated noise, to try to do nice noise. So the kind of diffuse effects are useful often, especially for the statistical point of view, and so you have nicer transfer operators and stuff like that. Okay, yeah, again, so basically a global picture. You have different noise regimes. So many people study small noise, and then everything looks deterministic apart from some little tweaks. That could be useful, but it's not so good to get the general idea of how noise affects the system, because you only look at some points of instability. And there's a philosophical problem that if you look at dynamics, as we know in deterministic dynamics, there's often problems at arbitrarily small scale. So if you make a small noise assumption, then the problem is that if you want this to hold, sometimes you need at every different scale, you need to have even smaller noise, and even smaller noise, because there's all kind of very small phenomena going on. So if you have some uniform noise and complicated dynamics, some chaos or something like that, you cannot, it is never really small, the noise. It's always relatively large. Of course, if you have super large noise, then it doesn't really matter what you do. You just smear everything out with the noise and you don't care. So the interesting part is where somehow this deterministic stuff connects to the noise and does something. And so we sometimes call this noise-induced phenomena. So, okay, let me immediately give you another takeaway message. I think it's not a good idea to think of systems with noise as a deterministic system with some noise. I think you should look at the system with noise. And there's a lot of, sometimes of course you have a deterministic system, you add some noise and you see that some things happen and connect. Ulrike gave some examples this morning. But it's sometimes also true that you have a system, you add noise and it does really different things. That was not at all in the other system. You couldn't see it as some kind of connection. So I'll try to give an example of that. Good. So how do we think about random dynamical systems? I think of it as a non-autonomous system. So a system that's driven by something. And then I hope that this driving has a probabilistic aspect that I can exploit. So here's a very simple example. I just iterate, and every time in the iteration I take a random vector from a ball, and then I add it on this function. But I can think of the sample of all these random vectors. I think of this as some time series of a system, and then of course the state space of the system is just basically the sequences of all these events, and then I just do shift dynamics on the base and so on and so on. So this is a canonical way. We can also do more complicated things. I don't mind, but of course if you want to do something specific, you often need to give something some structure to make it possible to analyze, but I don't think we should necessarily restrict to this. Of course the issue is that non-autonomous dynamics in general is rather complicated, and it could rather sensitively depend on the driving signal. So the people struggle with non-autonomous dynamics in general. And in some sense, the random setting is one where you would hope that putting some measure on the base that you could maybe say, you know, for except for a zero measure set of noise driving systems, I can maybe say something, and that turns out to be the case. Yeah? Of course, in the SDEs, we also have this driving paradigm, and then we just think of shifting on continuous functions, and then we have that all the measure sits on the discontinuous functions. So yeah, so it's a general path space, and of course the noise, the way where noise comes in is not in the previous description. In a probabilistic sense, it only comes in if you put a measure on the base. So we put a measure on the base, and that defines basically the nature of our noise. It says what is the probability to have a certain driving event. Yeah? And the hope, of course, is that we can do some kind of like for generic driving in the sense of for full measure set of driving realizations, we can maybe get results, and sometimes maybe for a little bit smaller set. But anyway, that's the idea in some sense. Good. So that's random dynamics. So random dynamics is sometimes non-autonomous dynamics plus some added tools that we can use to maybe to get some results. So, okay, so a lot of people, when they see SDEs and stuff like that, or maybe systems, they do transfer operators, or they do Fokker-Planck equation, these kind of things. And so mostly that then describes what I would call the one-point process, a one-point Markov process. And what it does is it's a time series model, probabilistic time series model for time series of the system. And often you can solve that, or you can do something there. But I just want to kind of make clear that in the dynamical system, there's more information than just in the Markov process. So a lot of people seem to say, oh, here's an equation, I write the Markov process, and then I can suddenly solve the Markov process. But there's a lot of information lost. So that can be good and bad. It can be, because then you say, oh, can I actually answer some question without taking care of all the other details? Or you say, well, I'm really missing something. So for instance, if you look at how two trajectories, two initial conditions move in the random system for some noise realization, then you can't do that with this one-point Markov process at all. So stability of a trajectory is also not measurable by such a Markov process. So you win some and you lose some, but there seem to be a lot of people that just basically jump immediately into transfer operator. And then they say, now we can understand everything. And I say, well, you can't. It must not be possible to understand everything because you throw information away. Yeah, so that's the issue. Of course, you can do other versions. You can also look at pathwise things and so on. But okay, this is just a warning thing. Good. So the central challenge is the following. Somehow can we study and understand random dynamical systems on par with deterministic systems? So now we don't understand deterministic systems so well, but we think we do, but there's a lot of questions there. But at least we want to get closer to each other, right? We want to say not if something with noise and we just throw our hands in the air and do something completely different. We'd like to kind of see if we can do similar things. And so in some sense, this is more like geometric or qualitative theory of random dynamical systems. So I'd like to understand the phase space of a random system. I'd like to understand what's going on. But we've already heard people struggle with that because sometimes when you make things not autonomous, objects disappear. That's not nice. So you need to kind of reinvent them. Yeah? The question is that possible? Can you recover some of these things? Or, of course, we saw some tricks. Sebastian put some singular limit somewhere, and then you have an equilibrium point somewhere, and then you're happy. Stable manifold. Okay, but let's just see here an example, a simple example of a system that has some maybe dynamics that maybe people don't know about, and I apologize for those who've seen it already a few times. So here's just some differential equation. Don't worry about it. It's some kind of, it has a Hopf bifurcation, so it has a stable equilibrium point for some parameter value, and if you change the alpha, you make the equilibrium unstable, and you get a stable limit cycle. And then we add some Brownian motions to these things, and it turns out that you can solve for the stationary measure in terms of distribution here explicitly, because it's one of these things with the potential, and you can just write this thing down. And so the interesting thing here is that you have parameter b in this equation, which is known as shear, and you look at this p, this probability density has no b. So we have now an interesting thing. We can play with b, and we leave the statistic from the one-point motion completely the same. So this measure is ergodic, and something that means if I want to know what is the average of the observation along the trajectory by Birkhoff-Ergodic theorem, I can actually just integrate over this measure, and then it's the usual thing we do in statistical mechanics. Okay, so here's the picture. So below we have the deterministic setting, so we have an equilibrium point that's attracting or a limit cycle, and then there's some distributions here that describe these things, and it can be done by stochastic analysis, the solution the Fokker-Planck equation. Okay. So now I just look at the situation where the alpha is positive, so I have this kind of little turbulent, and then I run two experiments with b is 1 and b is 20. There was a shear, and I just take initial conditions which are basically distributed along to the stationary measure, and I just run them forward. So we could call this a snapshot attractor. I'm aware from some talk some years ago. And you just run the points forward. You see that here everything goes to one point. There's a point. It's not a dirty spot. And here it goes to some kind of like object. But I'd like to kind of show what it actually really looks like. But this is just a snapshot. So if you just integrate it, and we look at the dynamics. So there's a lot of initial conditions going around, and the blue circle is the stable limit cycle of the deterministic system. What we see, it does some kind of dynamics. It looks very much like what we see in the deterministic system. It just doesn't shake so much. It's actually a non-autonomous version of stretching and folding, chaotic attractor. Yeah, so this is, and actually Sebastian saw this also years ago. It's some laser model, was it? Yeah, yeah. And so we see this picture, and the question is like, okay, what can you do? So if it's autonomous, we have some theory. If it's non-autonomous, random, can we do something here with this? Let me see. There we are. Yeah, so this is a snapshot. So if you change time, then this picture goes away, but it doesn't really go away. So one time if you do point equals to a set. And so it turns out that this ladder time is kind of like chaotic dynamics of some kind. So this is, and we will talk about that. And then the other thing is that everything is synchronized to a point, but this target point where you synchronize to moves because the system is non-autonomous. It's called some the random fixed point. So it's a moving target. You go fly after a moving target.
It would be nice to have a movie for the pointers, but
Yeah, yeah. Next time. Good. Yeah, because you see all these points, they just come there closer to a point. There's also interesting transient. There's interesting transient where you think you see this thing, and after a while it goes there. Yeah, that happens also.
This is plotted on with one. All the green dots see the same noise realization.
Exactly. Yeah, yeah. It's like I'm looking at phase portrait.
Yeah.
But it's time dependent. Some says I just follow the trajectory to see where they end up. Good. Okay, so the things like the Lyapunov response, I don't want to say too much about it. Some people know about them, some not. But some people believe that positive Lyapunov exponent means something like chaos. And so the nice thing is that Lyapunov response exists. So that's a good starting point if you want to do something. And there's an interesting result by Katok that says that in deterministic system, if you recurrence a positive Lyapunov exponent, you really have kind of like stretching and folding. You have transverse homoclinics, stable and unstable manifolds, periodic orbits, transversely insect. So this is, for people that know, this is basically, wow, we're just in a good setting. And so it's interesting because the Lyapunov exponent is a very local thing. It's ultra local. It's only just basically in the tangent space. It's only velocity vectors, but this is a global thing. So it's like local things cost something global. It comes at some price. So the question here that I'd like to answer, this is basically the first item. Can we study things by dynamical system methods? So can we understand synchronization? What are the characteristics of the synchronization? Do positive Lyapunov exponent imply chaos? If so, in what sense? So what is chaos in this random system? Just looking at the picture and say it looks chaotic is not good enough maybe for some people. We just had a whole argument here about definitions of things. And what are the characteristic features of roots to chaos? So how do you go from something which is synchronizing to something that suddenly looks chaotic? It goes like this. And can the Lyapunov exponents be accurately measured? That's maybe another thing. But if you think they're important, can we actually measure them? I would actually like to say, importantly, in this Hopf bifurcation example, even if we have a chaotic attractor which look chaotic and stretching and folding, the original system has absolutely nothing of that, right? It just converges to a limit cycle. Actually, you can even take just a stable equilibrium point and add noise and get chaos. So you don't need even a limit cycle. You can do it. Good, so I'm trying to answer some of these questions. Some results. So Julian Newman did a PhD with us many years ago, and he tried to figure out, I was shocked that it seemed to be not known, but necessary and sufficient condition for stable synchronization. It's the simplest thing. It's like an equilibrium point, unique equilibrium point for your dynamical system. You think, okay, that's the simplest dynamics you can see. The result is not super surprising, but I couldn't get the real experts to answer this question. And so we need to do. So there's two things you need. You need some kind of like approachability in a global sense. Points need to be able to come together. And then things like, for instance, negative Lyapunov exponent will do the trick. They will make you work. So second paper is something about horseshoes. So we can find horseshoes in random systems. And this is a special paper, other papers in preparation. Horseshoes in systems that have no periodic points. A random system has no periodic point. So there's no periodic point with a stable and unstable manifold. So I cannot define a horseshoe. But I can prove shift dynamics. I can prove that small lines become large lines. I can prove that we get actually the same thing as but without the periodic points. So here for the people that love the equilibrium points, the periodic points, the stable manifolds, you can have exponential growth of intervals without them. So usually what we use, we have a hyperbolic fixed point, and it becomes very close. It's very easy to see that things stretch, and that's what we use. But you don't need it. But of course you need to work hard. And it's interesting to see to what extent you can do things. So you can prove horseshoes without the usual.
So you mean horseshoes in a topological sense?
Yeah, so we can show that there's domains and there's symbolic dynamics on these domains and it's topologically conjugate. Yeah. And so in terms of the transition, so what's interesting, we can show that if you have transition from negative to positive Lyapunov exponent, we have something like intermittent dynamics, not in the 1-point motion, but in the 2-point motion. So it's actually the 2-point motion. What happens is that they start in a synchronization, they really cluster together. In chaos, they don't. And actually, just on the boundary, they start having this intermittency behavior. And this is the more generic property. So it doesn't, it has nothing to do with the 1-point motion necessarily. It's really in the 2-point motion. So that's a nice characterization. And yeah, but a bit different than maybe, did we come back? I was back here already, yeah. And then last paper, just an example of that you can actually rigorously compute Lyapunov exponents. And this is here for stochastic differential equations. With very high accuracy on the computer, which actually by hand you can't do. So by hand, it's very difficult to even prove that you have a system in SDE has a positive Lyapunov exponent. It's hard. But with computers, sometimes you can prove 10 to the minus 5 over a large regime with enclosure methods. So that's all, you know, new trend. People try to prove things rigorously on a computer with estimates and say you get 10 to the minus 5 accurate. That's pretty good. So that's also good for modeling. If you want to do something and then you're not sure that your numerics is okay, there's sometimes methods. Of course, there's some conditions you cannot always do it, but yeah, good. Okay, so this is some kind of quick overview over some things that you can actually kind of do something which you do in the deterministic case in some sense, and you can also do these things in the random case. Yeah.
About the occurrence of apparent chaotic behavior in the earlier case, you showed this happens for one realization of external forcing, right? So if you look at one, it could be just a protocol of forcing, and then you say, I apply the same protocol, whether it's random or not, it's not really relevant. The same protocol of forcing to all ensemble members, and I get this nice, I mean, what I see is some sort of energy transformation. I see it in this terms, or something, information is created. My question is, so that's for that realization, how do you get comparable properties from other realizations?
Yeah, so the methods of proof is so that it's true for a full measure set of full measure set of driving. So it's hard. You can of course find some that doesn't do it.
Yeah, no, sure not. But for full measure set of
Yeah,
drivers,
but it's also interesting to think if can you put conditions, because that says if the driving satisfies some conditions, that also in the autonomous case that you can basically not just say, oh, it's just some difficult condition. You could also maybe make something which is computable, or some driving that has a certain property where you say that it's enough. But yeah, the problem here is of course that yeah, so the proof uses a lot of ergodicity in the base, but you of course you can also work towards results that work. Say if my driving has certain properties, and of course it has to be long-term properties, then you could still maybe prove, because what you need to have repetitive behavior in some kind of recurrence, because you need to keep stretching things, otherwise you don't get exponential behavior. So these horseshoes, they have exponential stretching, exponential folding. That's the important thing. Yeah. Good. So transient versus asymptotic behavior. Well, of course, when we usually use noise and ergodic theory, we just have to average over very long times, and then we get well, extremely long dynamics, and often also in large domains. And yeah, if you have an SDE with this additive noise, we get with the whole state space is the support of the measure. And oh, I don't know how to switch this off. This is not so. Yeah, but it shouldn't switch off. Right? Yeah. So you have something with asymptotics or Birkhoff sums, but you also don't know how long it takes somehow. So there's some problems with. It's of course nice if you think that you have very long times in comparison, but as also mentioned before, timescales are important. So sometimes you don't really see these Birkhoff sums converge to ergodic limits at all. And it would be nice to know how fast these things converge, and there's some results here and there, some special cases, but not in general, not so easy. But of course it's an issue. But the point I want to make, maybe sometimes you really want to look more locally. You don't want to look at the big space. Even if you have a stochastic differential equation, maybe you're just interested in local thing. And we've seen this before as well. Some will talk about this trapping regions. You get trapped in some region for a while, and then you kind of go somewhere else. And that's interesting as well. So can you do something? But you can't really use the echodicity of the measure because the measure sits everywhere. So what can you do with this small thing? So what you maybe want to do is you want to compartmentalize. And maybe you want to average where you can average and not average where you shouldn't average in some sense. So if you stay a long time somewhere and you can say, well, I can say, take the average behavior, you want to extract it. But you need tools for that. So there are some tools for that. So I call this condition dynamics. I just put the domain. And I say, well, I'm just going to do statistics on this domain. Conditions for trajectory is conditional on the fact that they don't leave the domain. And this has been thought about before. So it's basically you get a substochastic process. You think if you leave, you just get killed, you have symmetry. And then you have something which is called quasi-stationary distribution. There's something where you converge to as a distribution. And associated to the eigenvalue of this state, there's also some escape time, that's well known. But what's less known is that if you want to do things about Birkhoff averages, this is not a good measure. Quasi-stationary measure is nothing ergodic. There's another measure called quasi-ergodic distribution, and that you can use to kind of also understand what are the Birkhoff averages over this thing. So you can compute these things. So in theory, these things look complicated, but if you do finite state Markov chain approximation of these things, it's just right eigenvector for lambda, the left eigenvector for lambda, and you take a Hadamard product, and you get all these things. So it's actually surprisingly easily to compute this on the computer, even though for the analysis and so you need to work a little bit harder. And yeah, so these things are well, then you can use them. So what I'd like to discuss is some way to use them. So one here thing is to get something which is called a local Lyapunov exponent. So maybe I'm interested in the Lyapunov exponent not in the whole space, going over the whole space, because the Lyapunov exponent says how do you linearly expand or contract over very, very long times, going everywhere over the whole measure. But maybe I'm just interested locally. So maybe you spent a long time locally somewhere, you want to know what happens. Is it actually converging locally or not? Okay, so here's a little movie. Oh, I think I should give the example first. Here's an example. This is basically like the Hopf bifurcation example. Look at the left-hand side. I just have two limit cycles. I have a stable point here, I have an unstable orbit here, and I have a stable orbit here. This comes over so-called Bautin bifurcation, doesn't matter. And then if you look at stationary measure, it has this Mexican head. It's not really Mexican, but it's what they call it sometimes. This thing with the double. It's a ghost. Ooh. Anyway, yeah, so you have to think of it rotating it around, right? Yeah, rotating it around. But then we can look at the dynamics. So what we're going to do is we can take two initial conditions in this inner circle, and we can let them run around and see what happens. So we do two-point motion, we do two initial conditions and integrate them. So here we're starting point for two initial conditions. I want to kind of increase this size. And so what we see is that they come close to each other. So there's a little tail, otherwise you can't see it. I plot a little tail. Now you see they're more or less on top of each other. So they really like each other. And here's, this is actually Lyapunov, this is finite time Lyapunov exponent plotted as a function of time for these trajectories. And now, what you see now, it goes outside of this circle, and now they somehow seem to not like each other. Now suddenly they separate, right? So oh, it's just the same as the E. It's just in the one as the E.
I mean, the separation is exponential now outside.
I don't. Well, yeah, probably, but I don't know. You see this. Yeah. This Lyapunov exponent looks positive. So the Lyapunov exponent for the whole system is positive, but for the conditioned Lyapunov exponent in this circle is negative. Well, you take out the whole system and you compute. The Lyapunov exponent is associated with an invariant measure, right? For the invariant measure of the whole system, but there's also a conditioned measure. And so what I do here, I basically average the process in the tangent bundle over the quasi-ergodic measure, not the quasi-stationary measure, quasi-ergodic measure. And then you get a negative value. And that says basically that if you stay very, very long here, then you would expect to converge to each other. And outside here. So you get information, dynamical information that's definitely not anywhere in a stationary measure. So solving for Fokker-Planck equations doesn't help you here at all. I think it should be interesting, because it's interesting to see if you have sensitive dependence on initial conditions or not. So here you don't have, because all orbits go to the same. You have sensitive dependence. You have dependence on noise, of course, because it's a driven system. But here you have sensitive dependence on initial conditions, here not.
get strong heterogeneity. So somehow it allows you to do a mesoscopic analysis of your system, not necessarily the global, not exactly the local, but it allows you to basically choose the region of your interest and define locally relevant properties. It seems very relevant to study then the finite time, finite.
You get stuck for a while here. We could see in the movie, you get stuck for a while inside. Yeah. I leave it to others to say whether this is useful. I think that sounds interesting to me, but good. Okay, so I don't know, let me look at the time. I think I can just scratch it, because Ulrike already mentioned this example. We look at here at a compartmental model for a noise-induced chaos for a standard map, for a logistic map. And we look precisely in the period 3 window, so Ulrike already mentioned that. And so what you do is so we add some kind of bounded noise in just some interval minus epsilon epsilon. And then what you see, here's the Lyapunov exponent, it just goes up with the strength of the noise. And Ulrike already explained that in some sense you know that there's also some chaotic dynamics here. It's just basically scattered around this basin of attraction of the period 3 cycle. You typically just converge to the period 3 cycle, but if you add some noise, you get some traction on this chaotic region. And the question is then, can you understand that? Can you understand why this Lyapunov exponent actually goes up? Or can you even estimate it somehow? And so we tried to do this with the compartmental model. And what we basically were interested in, we look at something with negative Lyapunov exponent, but we know that we have both contraction, but we also have expansion. And when we looked at the graphs here, this is graphs of time series of the difference, the log difference here of different trajectories, it looks like you go always up with one slope and you go down with another slope. So this made us think that maybe it's possible to find regions where you just expand, and maybe this is more or less uniform, and maybe when you contract it's also more or less uniform. Of course you don't know this in the first instance. And then what we say, well, so maybe what you do is you can find local Lyapunov exponents for these regions and try to figure out how long do you stay there, because you have two regions, expanding, contracting region, and you just average this with respect to how much time you stay. And this is these tolls, and these tolls come precisely from the quasi-stationary measure. So the quasi-stationary measure gives you this time, how long you spend in the compartments, and these other ones, they are averages over the quasi-ergodic measure. And you can do that, and what we then find is that it is not exact, but it doesn't look very bad. So we have a real curve. This is the real curve, I think, here, lambda, and this is the one you find from this very crude approximation, not that bad, I think, but maybe you can do better. But then we sort of like, does it tell us something about how this actually happens? So here we plot conditioned Lyapunov exponent here, and here the ones are in the domain, and here's the real one. So you see they're basically more or less constant Lyapunov exponents, so that's nothing happening there. But if you look at the tau, the escape time from the region, you see the one from the stable one comes down like a crazy. The one from the unstable region doesn't. So the reason why we get this noise-induced chaos is because we have a strong decline. So the stable region becomes super unstable due to the noise, and the rest is more or less the same. So the mechanism by which you get positive Lyapunov exponent really is because of that region. So you can see that in this way. It was just an illustration. But I think there's more things you can do in this sense to try to get some kind of sense where things are coming from. Because there's some things that's more like topological. You say, well, you can go to the other region, but you ask like, okay, is that going to be, is the chaos going to win it from the stability or not? And that's not clear. And it's not immediately the case, but there's a game going on, and you can estimate it, for instance, this way. So there's an idea that you can use compartmental models and statistics on the compartments in some smart way to do this. And this is, of course, a very simple example. Good. Now, it's interesting that looking at this quasi-ergodic measures, we thought it would also be interesting to look at quasi-ergodic measures on repellers. Now, the problem with transient behavior on a repeller, as also Ulrike was mentioning, is that, so how can you define, you say, well, there's a measure on this repeller. First of all, we don't know if there's a unique one or what's an important one. There may be many of them. And how do we define these things in terms of this escape? So there was this paper by Kans and Krasberger, that's of my childhood almost, not quite, but almost. And where they already saw these things, and they did great numerics on very old computers and stuff like that, and got some kind of like distribution of something they call natural measure. And it turns out that this natural measure is basically a conditioned quasi-quadratic measure that we also compute. And we can show that these things actually exist if these sets are hyperbolic. So if there's a problem, if these things are not hyperbolic, then the things may not converge. So this is always a bit, so in really interesting examples, maybe not, but in the logistic map, turns out that this set is hyperbolic, so you can do these things. So there's some paper here with PhD students and another paper coming out for hyperbolic case. Yeah, so I found it very nice that you can actually use this kind of like ideas here of random dynamics to kind of give, because they don't really look necessarily at random dynamics. They just look at samples and they sample things and they build up measures. But you can basically, well, you know, find a theory that justifies 40 years later that actually these things, you can make them rigorous to some extent. Good. So the rest of the time I want to spend talking about bounded noise. And so my take on this is that bounded noise is realistic in many circumstances. I don't think here that I have to fight with people over that observation, but there's some communities where people don't like this statement. And of course, the problem with the unbounded noise is that you can have severe, unrealistic, or unwanted consequences. So large noise events may be rare. That's usually what people say, oh, but it's very rare to have a large event, a strange event. But the problem is if you go time to infinity, then of course rare doesn't count. Rare will happen, and it may just dominate everything. So I like this idea that you sit here and you just transport it to Kerry's backyard in Australia by some teleporting. Gary? I was just talking about being teleported to Sydney in your backyard. But anyway, this may be an unlikely event in a stochastic dynamics model, which almost never happens. It doesn't happen in my lifetime. But if you take some kind of ergodic thing, and there may be a big sink in his garden somehow, that means I stay there, and there will be a lot of measure, even though I never go there. So we want to be careful with these things. Well, what I want is that I don't. So what happens with these SDEs is that I have a positive probability to go anywhere. Yeah. So I make a measurable set and I want to go there that has positive probability. I don't want that. I want that I can only go with positive probability to things that are basically close by in the evolution. And so it doesn't mean it's not a stochastic differential equation with sigma is bounded, because it still has its property. It doesn't matter what sigma is, as long as it's not zero. Okay, so what of course main advantage of this stochastic setup is that you can sometimes do stochastic calculus. Yeah, so that's very nice and that's wonderful. But it's very rarely that you can do that. So I think that it often has also complications also doing numerics and stuff like that if you want to do Brownian motions and stuff like that. So why do that if you don't need it? Good. And yeah, the disadvantage of the bounded noise is that you can't open a book and it tells you what to do. Yeah, so people say, okay, we can't do that. And I even, at some point I was speaking to some people also working in ecology and so on. I said to them, oh yeah, bounded noise, isn't that much more natural for your applications? And say, yeah, but if I publish something with a bounded noise in some simple model, I don't get it published in proper journal because they'll say I'm substandard mathematics or something like that. And this, one has to be careful for these traits. If some point people say the real noise is Brownian motion or something like that, one has to be careful with these things. Anyway, so I'd like to show you that you can do something. Of course, there's some boundary conditions, so it's not, you cannot always do things, but you can do some things. Good, so I'm going to talk about topological annealed set value dynamics. So with noise is essentially bounded. What I meant is what I just explained to Ingo, that you can, in one time step, you can only finitely far. Like for instance with the epsilon balls, I jump and I do an epsilon ball, I cannot go further than that. Then what happens, we can be eventually trapped somewhere, because it could be that my noise is there, but it is not strong enough to kind of leave a certain region. I can get invariant regions, and these invariant regions, if it's a minimal set, we can have stationary measures on them. So we have, we call this, and these sets, they're also then attracting, and they're attractors basically. So what you can see in such systems is you have a system with bounded noise. You think of a deterministic system, you add a bounded noise, you might expect different type of attractors to coexist. The attractors are now just basically sets, because you end up in the set, you can't leave. And then you go around the set and you just basically get some statistic of the stationary measure that sits in the set, that has support there. Now, if you change the parameters, then you can have bifurcations that these attractors disappear and appear and so on and so on. So what we do is we'd like to just look at the topology of these things, and I think that has some advantages. So if you look at the topological properties, you say just strip off all this probabilistic stuff. So we don't care. I just care that I can go somewhere, and then later maybe I worry about what the probabilities are. Because it's now interesting, because I cannot just go anywhere. I can go only certain places. So I can find little bounded regions, and I can try to see if the problem becomes easier. So that's what we want to do. We want to kind of track these regions, and maybe also, so what happens is this dynamics. If you look at all possible ways you can go, then you get basically set value dynamics. I think I have the next one. Yeah, here I have some example of two-dimensional map. I put lambda there because it just happened to be there, so don't worry about lambda. So I iterate a point with a map and then just add a ball. So I have a point, I add a ball, and then I do it for all the points in the ball. I just keep my mapping forward. And then I get some shape. Now, of all the points, I put balls, a new shape, and I keep going. Yeah. So this is my set value dynamics. It's an evolution of the system. And maybe this converges to some invariant set. Maybe minimal invariant set. And I can also, of course, look at single trajectories in these things. And so if you have a single trajectory, then typically this will end up in a minimal invariant set. But if I start with the set value system, it could just also end up in larger sets. Good, and so we want to look at the parameter dependence of attractor and its basis of attraction. So the basis of attraction are defined as all the points. If I start the set value dynamics, I end up in the attractor, for sure, after a finite number of iterations. So the difference here, these attractors for random systems, there's not that it's not like you exponentially approach them, because they're not really, you can actually map into them somehow. So that's interesting. They're a little bit different than the one in deterministic setting. Okay, so attractor is a minimal invariant set, and domain of attraction is defined. And I'm now going to show you a movie. So because that's what we did, we just make a movie. So here's a movie. And so what's here shown, the red is the attractor. This is a Hénon map, but this is the parameter value, which is basically boring. And then the black is the domain of attraction. So if I start in the black region, I will end up with the set value dynamics in the red region. And I change parameter. And so that looks nice, because I don't know anything about these sets. They look nice. It looks kind of smooth. It's continuous change, so some hope. Now it looks that you see that there's a little bit of kink appearing here. We don't like that so much, but maybe it's real or maybe it's not real, but it is real, unfortunately. It looks more and more real. Oh, and now suddenly it jumps. One attractor, and boom, it jumps into two pieces. Then we can forward, and you see this domain of attraction. Actually, here's this period 2 orbit of the system. It oscillates, but the domain of attraction gets this big split. And after a while, you see that they come closer, and hop, they jump again. Okay, so I think it's always nice to do this example. If you see this, you think, man, that can be understood, right? You must be able to understand this. You can't sit down and say, oh, throw the hands in the air. So the question is, like, what can you do here? Is there some singularity theory? This looks like just bifurcation theory, but just have some complicated sets. But the sets are not horrible. They don't look like fractals or something like that. They just look like blobs. And there's something about this red region hitting the boundary of the black region. You see that's when the thing pops through, where you have instability. So you pop these things through. Okay, yeah. So this was many years ago that we saw this for the first time, and then you don't know what to do. So let me try to tell you the story about that. So the main challenge of set value dynamics is naturally define that in some set of all compact subsets, because you just map from a set to a set, right? So you say, okay, but this space is very unpleasant because it has nothing like linear vector space structure. I cannot do continuation. I can do implicit function theorem. I cannot do anything. So I'm just really. So I have a nice abstract setup, as I'm just map sets to sets, and it looks like you cannot do anything. So this is something well known in control theory. People look at reachable sets, for instance, of controls, And basically people just run simulations. And that's what we did here too. We just run lots of simulations, you get some picture. But the question, can you do something or not? And well, we proved at some point here, paper 2015, that these topological bifurcations are indeed discontinuous. So they tend to kind of pop out, and so you can do that. But it doesn't really give us any clue of how to really understand if there's some kind of like typical ways in which these sets lose stability, or you can even see if the instability, where it comes from, or how to really identify these things. Until at some point we were sitting, and I still remember when it was, we were sitting somewhere and we tried, but we noticed if you have a boundary, and if the set is invariant, but it leaves also the boundary invariant, you have a system, some kind of dynamical system defined on the boundary. And so you can think maybe it's a circle. You think, oh, it's a circle map. So I can define rotation on the circle map. I see maybe bifurcations. So I see the deterministic thing. But the problem is, where is this set? So if you change parameters, the set moves. And how can you find it? So there was no information about that. You just know there's a set. But it turns out that if you just not look at the circle, but because you don't know where it is, but if you start with a point and you take derivative information, or here the normal, then you know something. So if it's smooth enough, then the normal really tells you where the rest of the boundary lies. So you have some kind of local description infinitesimally in terms of the points that you have and the normal. And then if you have, and if you look at now how a set evolves, it goes with this boundary map. So you start with a point, and the boundary has a normal. You map to a new point, then you put a circle again, and you know where you are. So where are you? Well, the nice thing is here that this vector precisely is aligned with this vector. So you just have to calculate this. You then normalize because you just interested only in direction. And you can calculate these things just by some derivative formula, and it just turns out that you use the transpose of the derivatives inverse. That's the one that you need to use there. And that's where you see how this normal vector evolves. So you have now a mapping that says it goes from the tangent bundle to itself. It takes derivative information into account. You map in this way, and of course the normal vector changes as well. So now we have a dynamical system that lives in a low-dimensional space. So if this is 2, then we have basically 3-dimensional space with the norm condition. And then, so now you have a deterministic dynamical system. So what can you do with this deterministic dynamical system? Does it tell you anything about how this has evolved? Well, it tells you that if I take all these points here, they all move forward by this mapping. So we have now some kind of deterministic system that maps things forward. So it turns out now, if you look at a set which is invariant, if the picture comes back up, you can read it as well, as I did. So the boundary of an attractor, so if it's a fixed set, then it must be invariant. So now I must have a boundary that's invariant. So what is an invariant for a low-dimensional system? It's just basically an invariant manifold. So these boundaries, they come from invariant manifolds. But in my space, say 2-dimensional space is 2-dimensional, but my dynamical system is 3 dimensions, because I need to kind of project down, because I'm not interested in normal information. Yeah, so I have something lying in 3-dimensional space, and if I project it down, I get the boundary. But these boundaries are manifolds. Hey, but now we're back in the comfort zone, because I can compute manifolds of finite dimensional systems. And I can understand what they do, I can understand the bifurcations, and so on and so on. So the instabilities and bifurcation of attractors of the set value system in this setting can directly be related to bifurcations of this boundary map, turns out. And the latter can be studied by traditional bifurcation tools like MatCont or COCO or whatever. And also interesting is that the boundaries of the basin of attraction also are invariant manifolds. These are not just invariant sets so easily seen, but it's more for the kind of pseudo-inverse. I don't want to talk about that. There's some kind of way to see this, that the boundaries of the basin of attraction are also invariant manifolds. So I'm going to happily study a low-dimensional system, look at these manifolds, project them down, and see what's going on with them. So how can you see which manifolds belong to whom? Well, there's different stability properties. So for an attractor, they are normally attracting curves, and for the boundaries of the basin of attraction, they are normally repelling curves. Okay, so we have a paper here that came out recently that basically does this in some kind of experimental way. So let me first give an example of the simplest case before we do other one. Here's the simple case where you see the 10 minutes, or you're a fan. Yeah. You're a fan. Okay, good. So here's a curve. Here's the T1R2. It's three-dimensional, so you have x, y, and an angle. Basically, and the angle, of course, is periodic, so it goes to pi, and then minus pi plus pi. So we have here two unstable, 2 points, and one is attracted. This is a saddle point, this is an attracting point, and you basically can construct a heteroclinic connection here that does all these things. So this is the boundary of the invariant set for a linear system here. Basically, it's an ultimately contracting linear system. Here's just a simple example. And then here is the associated curve in the space, and then you project this down to the xy plane, you see this thing. Good. So you can do something like that, and then, yeah, so this is the simplest example. Now, if you look at the Henon map, then we had this, it looks like this. So we had this bifurcation. Now here, there's some things going on. So what's plotted here is the red and the black, and then there's some yellow. The yellow is invariant manifolds, but you see there's some mess going on because actually the dynamics is not that trivial. It turns out that as soon as you have some kind of so-called wedges, it's not a smooth boundary. It has some kind of singularities on the boundary, and then these manifolds go inside and do some nonsense. And it can. This is a projection of three-dimensional stuff. Yeah. The kinks come from overlapping things. Yeah, so two things overlap and you project them down, you get these wedges. And so forget about these blue dots because that is not meaning. But here, these are things of boundary map. These are equilibrium points of boundary map. This one turns to light, but we focus on this one. So if I keep going, the parameter, oh, now I see something popping up here. So these are lines of some invariant manifolds that pop up in a bifurcation, saddle node bifurcation here and here. But I see the picture doesn't change just because my brute force numerics is much less precise than my dynamical system analysis. If I push it a little bit further, suddenly my white region appears. And that's precise, that's the correct one. So you see that this split comes up because there was a saddle node bifurcation with these manifolds, and these manifolds create boundaries of the attractor, of the basin of attraction for this, and it also then splits this big attractor into two pieces. Yeah, so we have here one piece together, and we get bifurcation here, and immediately the whole thing splits up. You can't just see it in the numerical analysis because it's brute force. And then we keep on going, and then you see you can just follow these things. So it's just illustration. So there's two things I want to illustrate. First, you can understand some of these bifurcations here as typical saddle node bifurcations with their manifolds. We can all do that. There's also the thing that you see is that still a large invariant set. There's still large invariant set, it's just not minimal. So the attractor sits here, but it's still invariant set, so you can still go here. It turns out that actually if you're here, with a point you do the set value system, you go to this entire set. Individual orbits tend to go here, but if the set value dynamics will go everywhere. So you also have a certain trajectory. So if you start here, you end up in this big set, and depends on the noise realization, you end up here. There's also a clear direction of transients. So it's not arbitrary. So if you're here, you go directly here. If you're here, you may go first to this whole thing, more or less somewhere. And if you end up in the black region, you will be committed to one of the two. So there is information in these pictures in terms of invariant sets. Minimal invariant sets are attractors, and their domains of attraction. They tell you what to go. It doesn't say when exactly it goes and stuff like that, but it says what's possible and what's not possible. Other things is just not possible. So there's a whole framework here of nested invariant sets that gives you this opportunity to look at these things. Okay. So what's behind this is contact geometry. Contact geometry. So it turns out that this mapping that we just constructed is a contactomorphism. And if we want to understand the dynamics and we want to understand the bifurcations and so on, so from a more qualitative point of view, we need to have a theory for that. So we need some qualitative theory of contact geometric dynamical systems, which doesn't exist. So contact geometry is some kind of like generalization of symplectic geometry in some sense, but it's not being done. So people study this a lot in wave propagation and stuff like that. So there's Arnold School, for instance, there's a lot of this stuff, but you cannot find really. So in improving properties of this boundary map and the manifolds, the specific ingredients on the geometry goes in there that shows that we actually have certain manifolds with certain stability properties and not other ones. So there's geometric information that goes into the other picture that I hid because I didn't talk about it. Another thing we can now do, we can show that we have stability of these things in terms of smooth stability because we can just use normal hyperbolicity. So if we have normally hyperbolic sets, in smooth theory, we know that hyperbolic things persist. We just push them out with this implicit function theorem. Yeah? So then we now understand also that some things cannot bifurcate when they're normally hyperbolic, and probably that they must bifurcate if they're not hyperbolic. So we know, and now where does the breaking of hyperbolicity appear? That's interesting. It appears somewhere on the boundary, but because we know the dynamics on the boundary, we also know where it happens more or less. It doesn't happen just arbitrary points. It happens at a point where you can break the hyperbolicity. So here's a number of papers about these things. Anyway, there's some technicalities, and so it's a paper by Jacopo as well. Good, I need to move. So I just want to kind of here as a more proof of concept show that you can do that for an interesting example. I'm just kind of wave my hand and show some pictures. So I just took a simple game theory model on the triangle. It's on simplex. Here's some equation, and why do we care? And I put some noise, and actually now the noise is such that this is the radius of the balls that I take for the uncertainty, but I make them even position dependent. So we can also do position dependent version of this, and the formulas are just more complicated, but you can still do it. And then we can use tools like mat, cont, coco to just basically understand the whole phase diagram of this thing. So let me just show, this is a paper that we're working on with Nero Lee. And so let me just show you, so here we have just basically, oh, and I forgot to put a picture. There's a phase diagram in the parameter space, and I'm afraid that I left it out. But these here, there are 21 pictures here of different configurations of invariant sets. They bifurcate one to the other, and you just can do it. So I will just show you can do it with some effort. It's not numerical simulation. I'm just doing bifurcation theory and tracking invariant manifolds and so on and so on, and I get invariant sets, and I can then interpret them. And I've in the parameter space, I have a complete picture of where these regions are. Okay, so what can you see in this picture? Here's just an example. So we have multistability here. We have different attractors. Each attractor has different domain of attraction, and we have also invariant sets that are not necessarily attracting. So you get some. So here's the picture overall in one of these numbers, and we have simple attractor with the domain of attraction. So here we saw such a shape before, and here's the domain of attraction. Means if I start in here, I will converge to this guy. I have same here. I have a region here. If I start here, will always converge to this guy. But I have also an invariant set here that lies here, and you see this invariant set doesn't lie in its own domain of attraction. The domain of attraction is here. So if I start here, I end up in this set. If I end up here, I go to here, right? Because that's in its domain of attraction. So this invariant set overlaps domain of attraction of another point. So I have a way to go from here. I go maybe here, but if I go here, then immediately I go there, eventually. So I have here a lot of pathways of the random system that tells you how I can move, and it's just precisely described in this invariant set. So this is numerically obtained, but not by trial and error, but just try to understand the structures. So most of the bifurcations in this system are simple. They're basically solenoid bifurcations, so that's why it's easy to do. There's just one heteroclinic bifurcation, which makes life a lot harder. So there's one transition which is hard, but the principle can be done. And I would say this gives a lot of insight, because if I now change parameters, sometimes I change the number of attractors or get some bifurcation, and then this phase portrait changes, and it means I have different behaviors. And so we have 21 different behaviors here in a small piece of the parameter space, and you can just analyze it with standard tools. Now, I think if you just do numerical simulations, you will see nothing. You have a hard time to understand what's going on, because you change parameters and it goes all over the place, or it goes to a place or not to a place. But this gives you a hierarchy of invariant sets and hierarchy of domains of attraction, and you can build a complete picture. Now, of course, for all these domains, you can also do conditioned measures, and you can do all kind of games, try to get better probabilistic information on these things. Yeah, good. So here, again, my take-home messages of the beginning. And we're going to have some salami. I was told it's very important. Everyone's looking forward. I have just 30 seconds or so. I wanted to make the point that we can actually study random systems like deterministic systems, just the dynamical systems, and the underlying deterministic dynamics could be very different from the random dynamics. So don't get tricked and try to understand random dynamics from deterministic dynamics, because sometimes it's possible, but often not. Compartmental models may be useful, And you can create reasonable comportamental insights by, for instance, look at these invariant sets of systems with bounded noise. It gives you a topological tool to look at things. And you can, on top of that, put other probabilistic things, for instance, with the comportamental models or other things. Yeah, okay, so that was my little summary of, and hopefully stimulus, if anyone's interested to try some of these things, or they think they have models they want to explore, very, very much welcome to collaborate or to help. Thank you very much.
Yes, I know that everyone wants to have some salami, and I'm happy to get the answer over the salami, but my question is just, so I know what this quasi-stationary measure is, but this quasi-ergodic measure, how do you get that? In a simple example, let's say.
Well, if you have a finite state Markov chain, you have a right and the left eigenvector, and you take a Hadamard product. That's how it goes.
Of the first subdominant, right?
For dominant vector. Yeah, but the thing is, you need to take track not where you are, but also how long you have stayed in the system. So there's information in the left in one of the eigenvectors of where you are eventually, because that's a quasi-stationary measure. But you also need to know how long you've been in the system, because you want to know something about average over trajectories. That turns out that that's what happens. Yeah.
With the boundary map, how do you analytically find the boundary map in an example? You want to do the bifurcation analysis.
Yeah, we have formulas for them.
But I guess first can you understand?
There was a formula. Yeah, there was a formula. There was a simple one, and then for the changing boundary, we have a complicated formula, but it's still formula. This one. This is my this is my boundary map. It has only known information. It has just.
Yeah, but to define it, don't you need the base of attraction, because you want to track the boundary of the base of attraction?
No, I just know that the boundary of the base of attraction is basically made up of invariant manifolds of this mapping.
Yes, but you're only interested in a specific one of those, which is the actual boundary of the base mapping.
Yeah, so if you look at the dynamics of this mapping, you can, of course, if it's very, very complicated, it can be somewhat difficult, but it's like if I have an ODE, can I understand its behavior? Well, if the ODE is sufficiently simple, I can more or less deduce that from numerical investigation and so on and so on. So here, if in this example, it's not so difficult to see where these things are. If you,
this is just a map on tangent bundles.
exactly.
But you're interested in a particular section of that, which is the boundary of the.
No. It's the projection. The section in the space. It's just a projection of the thing. Yeah, it's not. So I have no information here other than this thing, and this thing will tell me where the boundary of the set is, and also where the boundary of the domain of attraction is. In terms of invariant, so I have to kind of investigate: are there invariant manifolds for this thing? And then if they have the right stability property, there will be barriers. There will be barriers that make up divisions between invariant sets or domains of attraction of invariant sets.
Okay, but those invariant manifolds may or may not be boundaries of the basins, right?
If they have the right stability properties, they must be of some set, I think. Yeah. So it's not. So there will obstruction. So there will. It's not just they may. It's not. It's yeah. It's not. We're not at the level. So if you have an invariant set, then it's constructed. But I would say that for every right type of invariant manifold that you find, it must be part of some. It will form barriers. Yeah.
So you don't. It's sort of intuitive that the base and boundary is an invariant set, or invariant manifold. Did you also say that the boundary of the attractor is an invariant set?
Of this boundary map, yeah.
Okay, and
but it's not an invariant set for the system. It's not invariant. But it's forward invariant, because if you're in it, you're going to go out.
What's the argument? Like you have a proof, that's right, or is it just an observation?
No, it's a proof.
And can you maybe give some intuition how come?
Yeah, because you look at something which is a kind of an inverse of the system, but it doesn't have an inverse. So we call this a dual. It's basically an associated mapping where you think of the set value mapping, you try to do something that looks like an inverse. And this has also attractors. And they form basically attractor-repeller pairs. So the attractor, there's an attractor associated with the kind of inverse system, and the boundary of that attractor is the boundary of a base of attraction of another one. So it is duality. Yeah.
It's a lucky result. Yeah.
You have to be lucky in life. That's it. No, so the nice thing is that, of course, when we saw that we have one boundary map and it does a lot of things at the same time, you know you're onto something, right? So, because we've just looked forward, and then at some point we look backwards, and then we just realize that the same boundary map gives you all the information. So it's just wonderful. So you don't need to, yeah.
Thank you very much.